Make sense so far?
Yeah, I had a question.
Yeah, go ahead.
Like, can you show the above code which was in the Python? So over there, we know which variable is stored where and what is the scope. But now over here, which variable? Like now we have like %0, %1. These all variables. What are their scope and where they are stored in the memory? So the usage, like if some other dialect want to use it, so
Correct. So the thing is, and that's a very good point that you brought in, saying what is the scope, what is the lifetime, etc. All of this. That information is actually not shown here, but it can be attached as part of the IR, saying, um, I put it here. Let me see. I'm going to show you an example of new. Wait, I have LLVM nodes somewhere. Do you guys see LLVM? Oh, yes, right. Right. So you see this thing called LLVM attributes. So let me show you some LLVM-IR so that you know it sort of becomes simpler. By the way, you guys already should know about this. These are your front ends, this is your middle end, and this is your back end. Right? You should know this. So that's fine. Okay. I don't have like the actual LLVM-IR, but when you generate LLVM-IR, you will find at the bottom you'll see something like this. Attributes number 1. So for each instruction, you might have this annotation attached to it, saying that this particular instruction also has all these attributes. Now read one of them. Let's say you read no free. It's saying it implies that the function does not deallocate any memory. So this attribute, I can really tell now that it only applies to a function. First thing, it does not apply to an individual instruction in the function, but a function itself. So additional metadata that you would not see in your normal Python code, all of this stuff is also here. For example, memory none states that the function does not read or write any memory. This is a strong guarantee and allows the compiler to make aggressive optimizations. Getting it? So all this information is attached as usually an attribute to the thing. And in our case, if you go look at this, if you go look at our Pliron stuff, you'll be able to see that these instructions over here, generally, depending on whether or not attributes are present, you'll be able to see attributes assigned to them. I don't know if Triton has one. I'm not that well versed with it, but you can attach that, information, additional information that you want to attach to it. That's one way. I showed you an example for LLVM-IR. Something similar can be possible in other dialects of your IR.
yes.
Okay, and I'll show you what we're implementing as well with Cliff, which is Cranelift IR. We'll talk about that. Make sense?
Yes.
Right, we'll break in like 10 minutes. Okay. Any questions on this so far? This is making more sense now? Yeah?
Yeah.
Okay. So we already our idea is we can do this optimization and we're done. Right. Yes, Sharath, any questions?
Oh no, like I'm saying like when we write, when we do low-level programming for microcontrollers like that, we used to do with assembly language. Then like we'll write addition like using different. Then we'll try to optimize those instructions like to do it very.
That's one way of thinking about it. Correct. So you can always write assembly instructions and then you can do a naive implementation of it. A naive implementation simply means the straightforward way. I can just do A plus B and done, whatever registers and stuff. Or if I see that the hardware provides some extra stuff,
Extra,
then I will do some gimmicks to get that, to exploit that performance.
and there will be specific instructions to do it. Like then we can put that instead of.
It need not be specific instructions. It also can be the order of the instructions. It can also be, you know, the manner in which you write your assembly, right?
Yeah.
These things can have an effect because one is, it's very simple. If, for example, we discuss this a lot where we say, you know, how do we ensure that our cache is being hit all the time? So that the CPU, not talking about parallel processing, our CPU does not have to go all the way to memory and then pull that, you know, data or instruction. How do you keep hitting the cache? So you do what is called, you make use of what are called cache-friendly data structures. Technically what happens with modern CPUs is, if you lay out your data in memory, you know, in a linear fashion, the right word for that is, if you have memory data laid out contiguously in memory, when you access one element, when you do a single load, the CPU will go ahead and fetch the elements that are next to it. All right, this is called basically spatial locality, spatial and temporal cache locality.
Yeah.
Okay, it means that if you've loaded a value from this location in memory, it's possible that your next instructions may require data that's located close to it. Okay, so you pull that also into the cache.
Yeah.
So the next time you actually run an instruction, it's possible that, you know, you're calling it something close. Your instruction is going to be operating on data that's closer to the previous piece of data, and when it actually does it, it'll hit the cache, not the memory. This is a cache-friendly data structure and very simple. We've discussed this, if you remember, with what are called entity component systems. How many of you remember Baby? Game engine.
Game.
Hmm?
Yeah. Great game.
Right? They popularized it, at least in the game place, but the concept has been around for a long time. The concept is also known as struct of arrays or arrays of structs. Which one should I choose? Struct of arrays or arrays of structs? What they're indirectly referring to is, how cache friendly can I get?
Yes.
Make sense? Yeah?
In C, we do this using the register keyword that we say that we want to store this variable in the register. So always you read
That is volatile. So
volatile, you are saying?
don't
Not
optimize.
No, but register is the opposite of that. Over here, you say that if my variable X, I make it register.
Storage classes.
It will store it in the registers, not on your.
Right.
We have to do it very
Like
fast.
that is, you know, yeah, you want a particular thing, you want register level control saying this needs to be in a register, right? That's fine. Again, who honors all of that? Your compiler.
Yes.
Why will the compiler know that? Because, you know, you just gave it that attribute saying, okay, register matlab, this attribute matlab, follow that through the entire pipeline.
Correct.
Getting it?
Yeah.
It doesn't happen magically. The machine instructions need to be produced that will enable you to say that value is going to be in a register. Make sense? Right? Any questions? Because I don't want to jump into, like, I'll give you the brief summary of these things, what's going to come next, and then we'll get back to it. But any questions so far?
So C program is also using this thing. Yeah. Just off bit a question. No, but if a C program is using LLVM backend, then it has
Same thing. You'll also see that Cranelift, they're all backends. They don't care about what language is on the front end. A language is just basically a language. It's like, the language's job is, how do I make things easy for you as a developer at a high level, right?
Yeah.
And each language has its own pros and cons,
Yeah.
strengths and weaknesses, etc. Effectively, you as the developer pick and choose which ones work for you, right? Make sense?
So then you can use Pliron even in GCC.
No, with LLVM only.
Not really. Here's what happens. So let's say you got C, okay? C produced some intermediate representation, whatever. Produced LLVM-IR only, let's say. Okay. There is a dialect in Pliron that the author is writing that converts LLVM-IR into Pliron LLVM-IR. Pliron and LLVM. Get it? Then he does his optimization, he does whatever he wants with that inside Pliron. Then you can again produce LLVM only.
But this is just an
It's possible. He's doing that right now. Okay. Why are you doing that? It's because there can be multiple reasons. Once in LLVM, I'm not able to do some analysis and some optimization. So I want to pull it into Pliron, do my optimization, or do my analysis,
again spit out.
and then spit out LLVM-IR after that. Get what's going on?
Yes.
GCC don't follow LLVM-IR.
GCC has Gimple. Right? GCC uses this intermediate format. It also has multiple intermediate formats. By the way, don't assume that LLVM-IR is the only intermediate format. If you go and look inside, if you go and look inside the LLVM backend, that's why I said I'm not dealing with the shit. There's hazard things over there that we cannot deal with.
Yeah.
Okay, we don't need so much, right? So GCC uses something like Gimple. It is one of the oldest ones, so that's why it's not as modern. Like when LLVM came out, it came out with this brand new idea, saying what is called progressive lowering, or rather, the single IR format, and then being able to support multiple backends and stuff. Being very so LLVM's claim to fame was being modular. GCC's whole point was it is one single pipeline. Like you can't really hack around with a pipeline. You have to really have your own pipeline from beginning to end. LLVM said no, that's not required. You can do part A, front end, part B, middle end, part B, part C, back end. Make sense?
Yeah.
Yes? Any other questions?
And the HAR and THIR and MIR is there, right?
Right.
The HAR and these are like to follow whatever the rules we are putting to make sure that these rules are followed in this layers.
HIR and THIR are something very Rust specific that they needed. I'm guessing they needed to support MIR. Make sense? They needed that to support MIR. In fact, we will generate MIR once and see it.
Yeah.
Correct? Make sense?
It's like, there is type checking rules, one of the borrow rules are there, right? So like these rules, whether they are implemented properly, where the compiler will do checking.
Borrow checking rules is being done with MIR. Make sense? Okay. So, any questions on this? Nothing else? So, when we come back after lunch from our break, we will talk about the implementation details, because this is all just a rehash of what we discussed. Correct? There's no rocket science here. We've seen this. Basically, the reason I wanted to rehash it because I knew that you guys needed to put a mental picture together. So the rehash. Okay? When we come back, we'll talk about Pliron specifically. Okay? We've looked at MLIR. We know what it is, but we don't want to take a look at it specifically for the reason that I mentioned. It's completely in C++. The barrier to entry is pretty high. And you have to wade through a lot of stuff before you get to any meaningful, productive application. If you're not already part of that, so to be precise, if you're not already part of the LLVM ecosystem, that means you've not already been working in it, then this is going to be difficult, the whole MLIR thing. Pliron is the Rust alternative. One is it's pretty new. That also means that the drawback is a lot of stuff isn't there. Okay, the dialects aren't really there. But the benefit for that is we can pick and choose the ones that we want to work on and work on those things. And effectively contribute and also use it. Right? That's the goal. Next, so Pliron has some very important data structures. This is the everything from here on out is the Pliron framework. It's not a dialect. It's the Pliron framework. And I will show you one of the dialects that I have started writing, which is the Cranelift IR dialect. We all know Cranelift IR, right? Cranelift is another IR like LLVM-IR, but uses the Cranelift code generator, which is written in Rust, right? So I'm taking Cranelift IR, converting that to Pliron Cranelift. Okay? Once I'm in there, again, the next step is to do whatever you want to do and then produce Cranelift IR back. Okay?
But I thought we switched to Pliron now.
Yeah, we are.
So Cranelift is the backend, Pliron is the middle end, and
You can think about it that way. Cranelift can, because remember when we discussed this, when we talked about Cranelift, we said that Cranelift was WASM specific. All right. Cranelift IR is basically optimized WASM IR, optimized WASM code. That means it is converted to Cranelift IR after having already been optimized by the LLVM optimizer. In general, that's the flow that's the current. That's the current workflow that's being supported.
So after LLVM-IR, it goes to Cranelift IR, is it?
No,
LLVM flow.
right now, if you remember our previous discussion with one of the core developers, you remember that he mentioned right now the input when we actually get Cranelift IR, usually the case is that it's WASM code,
Yeah, it's
right?
WASM code.
But the WASM code is already heavily optimized and then converted to Cranelift IR. We don't do a lot of optimizations inside of Cranelift, is what he mentioned, right?
Yeah.
Yes?
Yeah.
Our goal is not to take WASM, but to take actual Rust code, which already exists. There is a Cranelift backend for Rust only, not WASM, Rust. There is one, but there's a huge performance penalty hit,
That was he was mentioning.
right? If you wanted to convert that, then one option is either you do it inside Cranelift, which is too difficult at this point, or you can pull it into something like Pliron, do what you want to do for what specific purpose that you want, because you can't do everything. But you might have a very narrowly scoped stuff that you think that you want to do it over there, and then
Give it to Cranelift.
push it back out to Cranelift IR. Get it?
Yeah.
Questions?
But why WASM came here? Like there is a MIR, after that Cranelift IR we can convert.
You should pay attention. Why did WASM come in there? Because we had a discussion with the core developers of Cranelift, where they said that Cranelift does not directly deal with Rust at this point. Cranelift's primary purpose was WASM. That's why we're talking about WASM.
But like when I see the Cranelift this thing, then they mentioned like it can be used as that compiler for Rust, right?
Yes, it can.
So
But
MIR
it
can
has
be
a
converted to
performance
Cranelift
is there.
Correct. MIR can be converted to Cranelift IR. That is possible today. That's happening today. But he mentioned that when you do that,
And in there we don't have that Cranelift IR optimizers. Like whereas in LLVM-IR we have
that's
optimizers.
exactly what we're saying. You get a performance hit.
Yeah, because of that we don't have that optimizers.
Correct. So the question to why we're talking about WASM, now you get it? So one is, if you have Cranelift IR, you can probably pull that back into Pliron.
Yeah.
Then whatever analysis transformation that I want to do or an optimization that I want to do can be performed there. And then I can split out Cranelift IR back again. So that I am not writing a code generator. The whole point about what we're trying to do is we don't want to start something that is impossible pretty much to achieve. Right? If you wanted to write a code generator, if you wanted to write an end-to-end optimizer, etc., it's a huge effort. We are making use of parts to get the job done.
Yeah.
Yes?
Yeah.
Okay. So last part. core data structures in Pliron, what we're specifically talking about is this is very specific to Pliron. Okay, that means the framework. In Pliron, as like MLR, you'll have dialects. How do you create those dialects? You use the Pliron framework to write those dialects, which is what I'm going to be showing you. Some of the important data structures in there, there's a data structure called context. The context data structure is what holds the entire IR related data. That means, let's say you have a function. Okay, this is a function. This is the function's type signature. This is the function's parameters, the parameters type signatures, the return type signatures, the body of it, each instruction within there, right? The instructions attributes, the instructions types. All this information is what you need to describe, or rather write. Make sense? You need to define, in other words. That's what context holds. Operation is the other important data structure that is defined in Pliron. The job of operation is what? It's basically anything to do with an instruction in other IRs like LLVM or Cranelift becomes an operation. In MLIR and Pliron, an operation can be much more than an instruction. That means if you have a function, generally a function is not an instruction, right? There's no function instruction inside Cranelift or LLVM-IR. But in Pliron or MLIR, a function itself is an operation. So the word, instead of using instruction, they're using operations. Okay? Like that, you can have your own types. You can have your own attributes. And then you can do your own passes. All of these things are what you can write.
Okay.
Make sense?
Yeah.
So the way this thing is implemented is what I'm going to be covering. There's something called generational arenas. How many of you have actually watched the video fully?
Arenas have a storage, mainly for storage.
Right. This is your storage space. That means I want to actually store what I mean by an operation. Okay, what should it look like in memory? Like when I say operation, what does an operation require? It requires operands. It requires returns, return value at the bare minimum. Then a lot of extra stuff on top of that. All that stuff, how do I store it and how do I retrieve it when I'm doing this analysis and this transformation? Right?
Yeah.
Here's what the context looks like. Just a brief glance, have a look at it. You can clearly see the context will have all the operations, all the basic blocks, the regions. This is a new concept inside of MLIR and Pliron. Regions are not present in other IRs so far. This is a very important concept also, we'll explain that. And then dialects. Dialects are already been describing so much of them. Then there's other kinds of stores, like very unique stores and all that you want to do. That's also here. Okay, and this is basically only available in testing. You don't worry about that. Got it? So we'll sort of walk through all of these pieces and understand how these pieces fit. Okay?
Yeah.
All right, any other questions so far? No?
No.
None? Okay, I'm going to stop.